Question 6. Okay, glycine is the simplest stable amino acid. So glycine, this is a structure given. So it has this NH2 and COOH. So for A, the isoelectric point of glycine is 6.2, pH 6.2. And define isoelectric point. It's quite easy. pH at which a molecule has a dominant form, which is a deuterium ion. Deuterium ion means the amino acid is present as dipolar ion. So means it will produce the ammonium and the carboxylate. Part 2. Draw the structure of glycine at pH 4. Already given, the isoelectric point of glycine is 6.2. pH 4 is relatively acidic compared to the isoelectric point. Again, so this one I already explained in the previous these videos. Okay, for this isoelectric point, if the pH is more acidic or relatively lower pH than the isoelectric point, so the amine group NH2 will react with the H plus because it's more hydrogen ion. It will form ammonium then. Then the carboxylic acid no change. At alkaline condition means the pH which higher than 6.2 now, it will be alkaline condition, and carboxylic acid will react with the hydroxide because under alkaline condition this one is more. Then the COOH will react with hydroxide to form the carboxylate and water. So because here is given the pH 4, again is relatively more acidic than the isoelectric point, means the NH2 will react. Means this group, the NH2 here will react with the H plus, will gain H plus to form ammonium. So means you just need to draw this structure. So you can give this one or this one. This is the answer in the mark scheme, right? So it will form this this ion. So the carboxylic acid no change. Only the NH2 now gains protons to form ammonium. Okay, part B. Figure 6.1 shows two syntheses start with glycine. Okay, so glycine is here. So let's start with this reaction 1. Reaction 1 is the bromoethane. Bromoethane. And after reactions, as you can see, there are two ethyl groups now is added. So means the two hydrogens here in the NH2 now is being substituted by this ethyl group. So it's something like this. The glycine, this is a glycine. So the two hydrogens will react and combine with the bromine to form HBr, and it will get removed. This one also, the HBr, and eventually a new bonds form between the C and N here and the C and N here, right, to form the compound here. If you still confused, you're not really sure what is happening, actually this is what you learned in AS last time. So let's say we have this chloro this ethane, so you can use bromoethane if you want. Okay, with the ammonia, so we will form this ethylamine and HCl. So basically it's just one hydrogens here, okay, combined with the chlorine to form HCl, and NH2 will combine with the ethyl group to form this ethylamine. Okay, so the condition and the needed is ethanol, heat under pressure. So means the solvent needs to be ethanol, heat under pressure. So this is the conditions needed. Okay, so this is the one that in AS, okay, which link or relates to this reaction 1. Okay, after that, so we have a reaction 2. Now the glycine is reacts and form this hippuric acid. So as you can see here, the amines now is form the amide. You can see. So means this is the groups that added, right, or that change. So later we'll see what is needed for this reaction 2, and after that we have this hippuric acid which form the compound U with excess of this lithium aluminum hydride. So this one we can discuss first lah. When we use lithium aluminum hydride, it will reduce two groups. It's able to reduce the amide here and the carboxylic acid. The lithium aluminum hydride react with this carboxylic acid is in AS syllabus, and lithium aluminum hydride with amide is in A2 or A-level syllabus. So now you need to use this reducing agent for these two groups. It's quite easy. So just focus on this carbonyl group because it's a reduction. So first it must remove oxygen, and this carbon will add two hydrogen. Then it will form this. It will form this CH2. Right. So means this carbonyl group will form this CH2. And for this amide, again, it will remove oxygen, and this carbon will add two hydrogens, and eventually it will form this CH2 as well. Right. So therefore, this is a product form, means the compound U. Okay, so let's see what they want. Part 1, state the essential conditions for reaction 1. So this one I already told you. The conditions for reaction 1. Reaction 1 is the bromoethane, which form this. So similar to the AS that you learned, the condition, it must be ethanol and heat under pressure. Right. Part 2, identify the reagent used in reaction 2. This is the one that we discussed just now. So we need to use, you can name this benzoyl chloride, or you just give the formula. So now, because it's a reaction between these benzoyl chloride with the amine. So see carefully. So one of the hydrogens here will of course combine with this chlorine to form HCl, and eventually this nitrogen will form a new bonding with this carbon, this carbonyl carbon. Then it will form this hippuric acid, right? This part. So this is how this hippuric acid form. Means for the reaction 2, we need to use this benzoyl chloride, right? Now for part 3, draw the structure of the organic product U that form when hippuric acid react with excess lithium aluminum hydride. Okay, this one I already told you how to produce just now. For this part 4, molecules of this phenyl aniline R can react with a molecule of glycine to form two dipeptide S and T. S and T are the structural isomers. So basically it's just the reaction of this the R, this one phenylaniline with the glycine. So let's say now I draw another glycine here. So it could be this NH2, this amine react with the carboxylic acid, or this carboxylic acid react with the amine in the this glycine. So eventually it will produce this one. So again this amine and this carboxylic acid, so it will form this this dipeptide. So this is a peptide bond. So after this these two combined, right? So it will form this structure, this S. Okay, if let's say now this amine from the glycine react with the COOH here, it will form the amide also here. This one, this after this react, it will form these amide groups. Okay, and eventually it will form this compound T, right? So they have different structure, as you can see. Okay, so this is S and T lah. Okay, part C. A student proposed a synthesis of hippuric acid by the reaction of the benzamide. Okay, so this one, and the chloroethanoic acid. The reaction does not work well because benzamide is a very weak base. Okay, part 1. Explain why amides are weak base than the amine. First, you need to know what caused the basicity. So it must be the lone pair, on the nitrogen. So whether it's more available or not, because the base is the one that able to donate its lone pair and gains the proton. So if the lone pair on the nitrogen is more available, means it's a stronger base. So the amide is a weaker base because, okay, this is a benzamide. So the lone pair on nitrogen, if you delocalize with this carbonyl group, means the lone pair here will move to the CN bond, and the pi bonds here will break and it will move up. The electrons here will move up to the oxygens. Means the lone pair here can actually move around, delocalize, and if it can move around like this, means it's less available. When there is a hydrogen's ion here, because it's not available, it's not likely to gain the proton, so it's less basic. That's how you explain. Lone pair on nitrogens is delocalized with the carbonyl, and this makes the lone pair less available to gain the H+. So therefore, it's a weaker base. Normally, we not really consider as a base also. Now, part 2. The pKa of the chloroethanoic acid is 2.86, and the pKa for ethanoic acid is 4.76. So pKa is slightly different from Ka because it's a negative log Ka, means when it's a smaller value, means it's a stronger acid, more acidic. So from this value, we know that the chloroethanoic acid is more acidic, and the ethanoic acid is less acidic. So explain the difference between these two pKa values. Okay, so first, you need to mention which one is stronger. So the chloroethanoic acid is stronger than the ethanoic acid. Why? Then you need to explain using the electrons withdrawing groups, the chlorine as electron withdrawing groups. So because chlorine is an electronegative atom, if you withdraw electrons toward itself. So there are two parts actually. The electron withdrawing, it will further weaken the OH bond here, or the after this OH bond break, it will form carboxylate here, right? So because the electron withdrawing ability of chlorine, if you let this negative charge with the carboxylate more, means it stabilize the carboxylate anion, means is less likely to bond with the H+. So when the H+ is more, then it's more acidic. Again, because of these electron withdrawing groups, so it make these carboxylates more stabilized. Means more stabilized means is less likely to bond with H+, because the electron density here is lesser. Less likely to bond with H+. H+ is more, then it will be more acidic. So that's the reason why, okay, we have this explanation. Okay, now for this part D, compound V is another amino acid. So we have this compound. So in this proton NMR, we shows a hydrogen atom in the 5 different environment. So we have A, B, C, D, E, which shown in this figure 6.2. So from here, roughly you should know what is the splitting patterns of this proton. Okay, so for this one is NH2. When the proton is bonded to this O, direct to O or N, all these protons, it will be a singlet. Just remember this. Means it will not have or less likely to have the spin-spin coupling with these protons on the adjacent carbon. So means the NH2 here is always produce a singlet, something like this. For this CH2, it will not couple with this proton, but it will couple with these two. So this one as one group will couple with these two hydrogen, 1 plus 2, it will form triplets. And this one also, this one as one group, it will couple with these two hydrogen, 1 plus 2, also it will form triplets. So means C and D both will form triplets. Of course, their chemical shape is different, right? Because this CH2 is near to electronegative atom, it will be what you call different values later. So we have later we will use the tables to further explain. Okay, so these 4 protons in the benzene ring, you just remember whenever proton in benzene ring, it will give multiplets, right? So this is B, the signal B. For this COOH, this one is alone, so it's always singlet, no spin-spin coupling. Okay, so now roughly you should know the splitting pattern, and later we will talk about the chemical shift, the values. What is a ppm? Okay, so now let's move on. Okay, we will check one by one for this carboxylic acid. Okay, so it's A. A is carboxylic acid. The chemical shift is 9 to 13, right here. This one, A chemical shift is 9 to 13 ppm. Okay, how about B? B is the protons with the benzene ring. Okay, B. So the proton attached to the aromatic ring, so it's 6 to 9 ppm. Okay, how about the C? C is this. C is the proton next to the aromatic ring. Okay, so this is C. Alkyl next to the aromatic ring, so it's have a chemical shift 2.3 to 3. Okay, now D. D is the one that I told you, the alkyl group that next to electronegative atom, D, right? So the chemical shift is slightly higher, is 3.2 to 4. Okay, now E. E is the alkyl amine, so means the proton next to this nitrogen, means this one, right? E. So the NH2, this proton will give the chemical shift about 1 to 5. So this is the how you use the table to check the chemical shift. Of course, the splitting pattern you cannot check it, but the chemical shift you always can. Okay, so if you understand what I told you just now, okay, you just fill in the blank here, right? The chemical shift for all this. So for the carboxylic acid, okay, this chemical shift. Benzene ring, this chemical shift. Okay, the C, this one is the direct to the alkyl group to the aromatic ring. Okay, this one is the alkyl group with the electronegative atom. This is the protons in the this amine, right? So singlet, triplet, triplet, singlet. Okay, the last part completes the table 6.3, placing the tick to indicate any protons whose spread are still present. Must be careful, still present in the proton NMR. When the V dissolve or react with this D2O. Okay, so let's check the structure again. When we mix the D2O with this V, so the OH and this NH, they all will exchange with the D and D. So eventually it will form COOD ND2, means it will not really produce a signal. So means these two signals will disappear, and it will only remains this three, BCD. So you only put these three, put the tick here for the BCD. So that's the answer. So just remember, COOH and the NH2, the protons will all this hydrogen will exchange with the D, right, and it will disappear. Okay, that's all. Thank you.